All right, so this is a lesson in which we introduce the key aspect of integral calculus, which is an integral. And the title of this lesson is the definite integral. So I'll get straight into it, really starting with a continuation of the last lesson, in which, remember, we have a graph here of y equals the absolute value, the square root of x. And we're looking at this, determining this shaded region between the x-axis and this curve between, in this case, 0 and 4. And that's what you see there. Hopefully that sounds familiar. And then we kind of ended off, or one of the last parts of the last lesson was looking at this, what we call a Riemann sum, which is the idea of finding the area of all these rectangles. That's the height, and that's the width, in this region, this interval from 0 to 4. But the idea is, if we want all these rectangles to be, as accurate as possible when I add it all up to find the area, I want to have as many rectangles as possible that are as skinny as possible. And that's what we're kind of looking at here. As the number of rectangles, n represents the number of rectangles here, as that number gets larger and larger and larger, the width of each rectangle gets skinnier and skinnier and skinnier, the change in x. And as we approach infinity, as you have infinitely many rectangles of infinite thinness, then this sum approaches the exact value of this area. And again, that was really a review of what we talked about last time. However, all of that there can be summarized using this different notation, which I think is more pleasant and we'll be using going forwards, which is called an integral, or a definite integral. And so if I zoom in on this, these two expressions are equivalent. And so, first of all, this symbol here, which looks kind of like an S, and it's meant to, you can imagine it being an elongated S for sum. And this here, that's a kind of like essentially a Greek letter S. That's in the letter sigma for going back to sum. So they are related to one another. But this is representing the sum of all these infinite rectangles from 0 to 4 for this particular function, root x, which is what we have graphed right here. And the dx right here, maybe I'll change my highlighting here a bit. The dx, that kind of represents the change in x. Essentially what we have here is we are still finding the area of all these infinitely many rectangles. This is the height of each rectangle. And notice, if I imagine each of these vertical lines I drew being a very skinny rectangle, the height of each would be the exact same as just the output of root x at that particular point. And this here represents the width of each rectangle. That dx, which is getting infinitely small. And notice that notation dx should look familiar, right? Derivative, one of the common notations is dy dx, in which we imagine this being the change in height, the rise over the run. And the run is getting infinitely small. We can see this connection starting to come up. And the dx we see in a derivative and the dx we see in an integral are essentially the same thing. It's just change in x that's getting infinitely close to 0. And so this still represents, in essence, this infinite number of infinitely many, infinitely skinny rectangles beneath a curve, or between the x-axis and this curve. And that represents, again, a sum of these areas to create this total area that we have shaded right here. And so with that said, if we think of an integral like this, now that we've introduced to an integral, then what happens when the curve goes below the x-axis? Like this. So I have some function here. And in fact, the function, you see this line in red, the equation of it is negative x over 2 plus 2. Right? That's the function that's in red. That's also the same thing we see right here. When we start looking at curves or lines or functions that go below the x-axis, the area is still between the x-axis, but now it's above. And we call that a negative area. So if we look at this particular example right here, notice the areas that are shaded are from 0 up to 10. And that's what we see in my integral right here. From 0 up to 10. And so what you see is a visual of this integral right here. This integral right here is describing the shaded region from 0 to 10 of this line. And essentially, again, this part that I've highlighted in yellow, well, that's not a highlighter. This part that I've highlighted in yellow, that is, yes, the equation of the line that I gave you, but it also represents the height of all these infinitely many rectangles at any given point. that eventually go into the negatives. And so this area I'm kind of drawing in red represents a negative area. And again, this dx represents the width of those infinitely many rectangles. So how do we find this? Well, I can evaluate this particular integral quite nicely, because if I look at my visual, I just have a couple of triangles. I don't need to do anything beyond finding the area of a triangle. And so the area of that particular triangle there is base times height divided by 2. So in this case, the base is 4, the height is 2, divided by 2, we get 4. So that's the area of that region that's kind of shaded in blue. And then over here, this region here, area of this is base times height divided by 2. So in this case, it's, what is that, 6? Yeah, 6. Well, that's a weird looking 6. 6 times 3 divided by 2, which is 9. But that area, again, is below the x-axis, so the area of that is negative 9. So looking at all this together, just clean this up a little bit. Looking at all this together, the total area of these two regions together is going to be negative 5. 4 take away 9. Or the value of this integral is negative 9. And so going forwards, when we're dealing with an integral, a negative value makes sense. A negative area makes sense. It represents an area below the x-axis. Or in this case, it represents the sum of these two areas, but the area below was greater than the area above, so we have a total, altogether we have a negative area. All right, so with that said, that's mostly the point of this lesson is to get familiar with this notation of an integral and some consequences of it. So what I have here are a whole bunch of things I want to generalize. So first, in general, if you want to find the integral of any function, and again, dx, that you'll always see that notation there. That represents the width of any rectangle. This represents the height of the rectangle. But in general, if you want to find it from a to b, these are just some numbers, some starting point and ending point. If you want, you can change the order of those around and go from b to a, as long as you change the sign of the whole thing. So any given time, you can change the order of these of the interval. You can change, essentially, it's kind of like imagining looking at the interval backwards or in another direction. And if you do that, your sign changes of your integral. What if you want to find the integral of some function from a to a, the exact same number? Well, that means you're finding the area of some region that has no width, because it's the beginning point and the ending point are the same number, which means I don't care what the function is, this must equal 0. What if I want to find the integral of some parameter from a to b? But this time there's also some constant here, c representing just some constant. Well, as with the derivative, constants are quite lovely. Essentially, if you think of it in terms of area, this constant is kind of stretching or compressing the height of this region, which means it's just making the area some amount larger or smaller depending on c. So really, I can imagine this equivalent to being to this as just c times the integral of a to b times f of x dx. And the same thing we dealt with when we were differentiating. If we had a constant, we could just not completely ignore it, but we could just cast it aside and focus on what really mattered, the part that varies. Sorry about that. All right, what if we are finding the integral of a couple different functions? A to b again, but a function f of x plus or minus g of x. Well, as you can perhaps guess, I can just look at each of these integrals separately if I wish. So this is equivalent to the integral of a to b of just f of x dx plus the integral from a to b of g of x dx. Or I should say plus or minus, depending on what operation we have there. All right, now for this one, and notice we have the same function each time. we have f of x dx, f of x dx. But if we look at my interval, I go from a to b. And the next one, I go from b to c. So really, I have the same function, two different integrals, but the endpoint of one integral connects with the beginning point of the next one. So if it's the same function, this must be the same as a single integral from a to c, whatever these numbers are. And again, this is only true if these two integrals kind of connect up to one another. That's essentially what we have here. This is the shaded region of one portion of another, but they are right beside each other. So we can might as well treat it as just one singular shaded region. Lastly, even and odd functions. Haven't really talked about these in a while. If a function is even, that means it's symmetrical about the y-axis. So for example, a nice example is x squared. X squared is even. And so if you have an even function, any even function, and you're going from negative a to positive a, that means you're going from some number over here to the equivalent number over on that side. Well, if it's symmetrical, then these two regions must be the same. So really, this must be the same as finding the integral from just 0 to a and then doubling that. So I'll put the 2 first. And quite often, if something is an even function, it's nice to deal with the number 0. And again, these are always equivalent. If something is an even function, and again, my example was this quadratic function here. If you're going from negative 5 to positive 5, if you want, you could just find the integral from 0 to 5 and then double your answer. And what if the function is odd, but we're going from negative a to positive a? Well, then this, I know this must equal 0 no matter what. And why is that? Well, let's think what an odd function looks like. For example, here's an example of an odd function, x cubed. And so if something is odd, that means the region over here must always be the same as the region over here, except one side will always be positive, one side will always be negative. And so the two will always perfectly cancel each other out if it's odd. OK, so like I said, the majority of what we want to focus on is developing a feeling for what this notation means and what it represents. Just like when we first started dealing with derivatives, that was our focus. And now you probably don't have to really think about what a derivative means. It's become probably somewhat innate. And so if I look at here, I got this function f of x. So let me label it. See, my function starts off here at negative 3 and ends at 10. OK. So what I want to do is I want to use this graph to answer these 3 integrals. Now, let me go back to what the title of this lesson was. The title of this lesson is what we call a definite integral. And a definite integral is what we've been dealing with. A definite integral has a definite starting point and ending point. And every example we've looked at today has been a definite integral. They've always had some number here to some number here. An indefinite integral doesn't have those, and we'll look at those in later lessons. But a definite integral is, again, essentially finding the area from some starting point to some ending point. So looking at this first example down here, and to be honest, I would highly recommend you just pause this and try this on your own first, because really from the graph, there's no new concepts I have to show you. It's just a matter of just trying it. But if I look right here, I have an interval from negative 3 to 4. So looking at my graph, negative 3 is right here, 4 is right here. So I'm trying to find the area of all of this. In fact, I'm going to break it up into a few different shapes. I want to find the area of this rectangle right here. I want to find the area of this triangle right here. And I also have this little triangle right here. OK, so that's, first of all, what I'm trying to find here. That's the first hurdle. OK, how do I find that? Well, I just got a bunch of very simple two-dimensional shapes. The area of that part in green I can see is 4 by 5. So this is, whoa, come back. This is 20. Now, for the area of these two triangles, there's a few ways of looking at it. I could find the area of this triangle here, find the area of that little triangle, and just keep in mind the little triangle will be negative, the larger one will be positive. And that's perfectly fine. Or what I'm actually going to do, because I feel a little lazy, if I zoom in here, I can just see that this little chunk here and this little chunk here are going to cancel each other out. the exact same area. I can just see it. Just one's positive, one's negative. So together those make a zero pair. They're zero. And so I'm just not actually going to bother calculating that part. I'm just going to focus on this part right here. And if I look at that part right there, in fact, if I break it up again, I have another area of 2 right there. There's a little rectangle with an area of 2. And then this triangle up here is 2 by 4, 2 wide, 4 high. And so 2 times 4 divided by 2 must just be 4 units. And so altogether, that shaded region, or the region from -3 to 4, must be 26. And again, if you daydreamed for a bit, you may go, well, how come my graph is only going to -3? Even though here it should go, sorry, whoa, I'm the one daydreaming. If this is only going to 3, how come that has a 4 there? Remember again, I chose to logically ignore this last part because I could see those two are going to cancel each other out. Either way, you'll still get to the same answer, 26. Okay, next I want to go from 10 to 4. Notice I have this larger number at the bottom. So one way of looking at it is that's me going from here to here, but looking backwards. What does that mean? Well, it's probably a lot easier to take into account something I mentioned a few minutes ago, and that is to rewrite this as integral from 4 to 10, which we can do as long as I just change the sign of it. And now this is what I want to focus on. From 4 to 10, and at the end I'll just make it all negative. And so looking from 4 to 10, that's this region all right here, which I'm going to break up into 2 parts, a rectangle and a semicircle. So if we look at the rectangle portion, it's pretty nice and easy. It's 6 times 1, so that's just 6. And then I have the semicircle here, which area of a circle, pi r squared, pi times 3 squared divided by 2. And so put all that together, I got 6 plus, what is that? 6 plus 9 pi over 2. Well, that's almost it. Keep in mind, that's the area from 4 to 10. 6 plus 9 pi over 2. Don't forget, though, the question was asking from 10 to 4. Or don't forget, there's this negative right here. And so in the end, I need to just make all this negative. Now we're done. All right, that leads me to the last one, which is from -3 to 10, which really at this point, keep in mind -3 to 10 is all of this put together, right? Or actually, I should say, take that back. It's all of this kind of put together. Because again, -3 to 4, I figured out was 26. 4 to 10, I figured out was just this part. And so -3 to 10 is all that put together. And so the only thing I can avoid this time is I don't need to think about this negative here. Because again, that negative there was me going from 10 down to 4, which again is a little bit weird to think about. And so in the end, I can just see. Actually, I was just about to make a mistake, but I'll say it anyways. I can just see this is going to be the same as 26 plus 6 and 9 pi over 2. However, all of that right there is me forgetting about there's a 2 right there. And so that said, that's easy for me to take care of. I can just think of this exact same question I gave you as 2 times the integral from -3 to 10 times f of x dx. And so this right here is all of this, just those previous 2 areas put together, all times by 2. There we go. Now I've got it all sorted out. And again, I can simplify this more, but I don't really care. All right, so again, before I move on, everything right now is about understanding what this integral notation means and what it reads. The actual calculations are right now mostly just a matter of looking at triangles and circles and rectangles. That's not meant to be what our focus is really on. It's what does this notation mean? What does a negative area mean, and so on. That leads me to the last part, which is a lead into the next lesson, which has the same initial function, f of x, And then I have another function which is based on it and an integral. So again, this is f of x. Again, it's the exact same function we're starting with. But this time I have this new function, g of x. And what is g of x? G of x is the integral from -3 to t of f of x dx. So g of t is this. All right, so I will say, if you already understand what this means, which I don't expect, but if you already understand what this means, this is an incredibly easy question. In fact, all of these are very easy. But the first one you can do in a few seconds. But what does this mean? So again, I would encourage you to try this on your own, but first keep in mind that this function f of x right here, I see right there, but g is the integral from -3 to t. G of t is the integral up to t. And again, for this first example, t is 0. So what does this mean? Again, I'd recommend you try it, even to make even if you're sure it's wrong, and I'll work it out in just a moment. All right, so what does this mean? Well, maybe it helps if I write it out like this. It might help if I write it as the integral from -3 to 0, because t is now 0, of f of x dx, which means the area of this function from -3 to 0, which is this, -3 is right here. 0 is clearly labeled, so it's this region right here. That's what we have to figure out. Again, the hard part is not calculating the area of that. The hard part is understanding what all this means. And that's what's being described here. G at 0 represents the integral from -3 up to 0, this time, of this curve f of x. And so if I look at this, I can just see right away, that's 3 times 5, that's 15. So this g at 0 equals 15. And so g at 1 is going from 0, sorry, not going from 0. G at 1 is the exact same function here, going from -3 up to 1 of f of x dx, which really means I just need to look at, I'm going this far now, all the way of all of this, from -3 up to 1. And again, the definition of g of x is that it starts at -3 for this particular example. And so this is no longer 15, this is now 20. And g at 10, that means the integral from -3 to 10 of f of x dx. Well, hey, that's exactly what we were doing right here, without that too. And so this must be the answer. So again, all of this here means what I figured out highlighted in green right there. So I guess 32 plus 9 pi over 2. And that's where we're going to stop. Okay, so to wrap up, just keep in mind, I'm guessing there's some parts of this lesson that were challenging, but not the calculations. I mean, really, I'm just mostly finding areas of circles, rectangles, and triangles. So there's a lot of abstract aspects to this lesson, but there's also a lot of really concrete parts. Like I'm just finding quite often the area of these basic shapes. And so it's this weird mix of being really concrete, finding the area of triangles with really abstract.